Hello, and welcome to the Symphony Analytics demo. In this video, we'll be using tools available in the Symphony Analytics pack to analyze some CAN data. We'll learn how to upload files into HDFS. We'll learn how to upload, view, modify, and create tables with an Apache Hive. We'll perform simple analytic functions with Apache Pig, and we'll perform simple analytic functions with Apache Spark. The example and the files we'll be using today can be found at the Hortonworks website shown below. Let's get started. We're going to begin from the Symphony homepage. This page is available from all user workstations. To reach Mbari, you can either click the link under the Mbari section or click the drop-down from the UI. The first page Mbari brings us to is the metrics page. Here we can check our cluster health and see any alerts that have been triggered due to resource usage or services becoming unavailable. Let's start by uploading two CSV files into HDFS. To accomplish this, we'll go to the Files view of Mbari. Here we'll get a visual representation of our HDFS directory structure. We'll go to the user directory, and since we're logged in as the admin user, we'll go into the admin user's user directory. And then in admin's data folder, which is where we'll upload the files. To upload a file, simply click the upload button in the top right corner of the screen, then click to browse local storage. We'll be uploading both geolocation.csv and trucks.csv. Since we can only do one at a time, we'll start with geolocation.csv. And now trucks.csv. With our CSV files loaded in HDFS, we can now start to load them into our Hive database. Let's switch to our Hive view. In the Hive view, we can add, remove, query, and upload tables into Hive databases. We perform queries in the worksheet provided, and we can view our available databases here on the left. First, we're going to query our default database for any existing tables. We see that there are none. Let's upload the two CSV files we just put into HDFS's tables. To do this, we'll click the Upload Table tab. Before we upload any CSV files, let's click the config and check the box for is first row header, because the first row in each CSV file is indeed a header. We'll want to upload from HDFS and give the full path to the file. When you have the full path, click preview and it will show you what your uploaded table will look like. As we can see, the first row of the tables have been successfully converted to headers. This looks good, so we'll go ahead and upload the table. When we do this, in the background, a temporary table is created. The data in the CSV file is uploaded to it, and the data from the temporary table is then loaded into the actual table. Now we'll load the geolocation.csv file in the same manner. Once again, we'll hit preview and see that the table headers were created successfully and that the table looks ready for upload. Now that our tables are uploaded, let's take a closer look at what's in them back in the Query tab. Let's perform our Show Tables query again. We see that both our geolocation and trucks tables now appear in our default database. Now we'll take a closer look at what's in each of these tables. Let's list 10 entries from the trucks table and get an idea of what's in it. The trucks table lists a driver, a truck, the truck model, and a monthly entry of miles driven and gas used over the course of about 3.5 years. Now let's list 10 rows from the geolocation table. In this table, each row lists a truck, a driver, an event, and the geolocation information for where each event occurred. Each recorded event will either be a normal beacon event or an event that was recorded because safety parameters were breached. For example, this overspeed event was recorded because the driver exceeded the speed threshold for the location. Now we're going to create a brand new table from trucks called truck mileage, which will give us the miles per gallon for each truck every month. The table appears to have built successfully, so let's take a look at what's in it. Each row of our new table will list a truck, a driver, a month, the total miles traveled for that month, and the total gallons of gas used for that month. The table also contains the miles per gallon, calculated by dividing miles traveled by the gallons of gas used for that month. Let's create and save a query that will calculate the average miles per gallon. From truck mileage, we'll take the average miles per gallon and then group it by the truck ID. And we'll go ahead and save the query as average MPG. To access a saved query, we can go to the Saved Queries tab. From here, you can click on the name of the query, and it will give you a new tab in your query editor containing the query you saved. Let's run it to see our results. Here we can see that the average miles per gallon were successfully calculated out for each truck. Now we're going to perform a Create Table As Select to put the results of our average miles per gallon calculation into its own table called average mileage. We're going to store the results in ORC format and do the exact same query from the average MPG query we just saved and ran. The table appears to have been created successfully. Let's verify its contents. We can see that the table appears to have been populated as expected, with an average miles per gallon listed for each truck. We'll now perform another Create Table As Select and create a table called Driver Mileage, again stored in ORC format. This table will sum up the total miles for each driver and list each driver and the respective total miles traveled on each row. And again, we should verify the contents of this new table after its creation. As expected, in each row we have a driver and their total miles traveled. Before we move on to our next tool, we're going to create an empty table called Risk Factor. The column headers for this table will be driver ID, events, total miles, and finally risk factor. We'll now populate our risk factor table with a pig script. Let's switch to the pig view to begin. We want to create a new script called riskfactor.pig. To work with Hive tables, we'll have to load them using the hcatalog Java package. Create a variable A and go to the pig helper dropdown, followed by hcatalog, and then select the load statement. This line will load the specified table into variable A from Hive. We want to start by loading the geolocation table. Let's create a new variable B, and then go to the pig helper dropdown again, go to relational operators, and select filter. We're going to filter variable A, and the condition will be any event that is not normal. If you'll remember, the geolocation table contains several rows of events and locations that they occurred. This statement is simply filtering out all the normal events, leaving us with just a list of safety breaches and the locations they occurred. Now let's create a variable C. Go to the pig helper dropdown again. Go to relational operators and select the first for each statement. We'll be iterating through the rows in variable B, which contains all of the events that are not normal, and creating new data from those rows. The new data will be the driver ID, the event, and a new row called occurrence, which will simply contain the integer 1. Now let's start making some sense of this data. Make a variable D, go to pig helper, go to relational operators, and select group var1 by var2. var1 will be C, and var2 will be driver ID. We're now grouping all of our occurrences in C by driver ID. In variable E, we will iterate through our grouped entries in variable D using for each. We will then sum up all of the occurrences for each driver together, giving us a list of drivers and a total number of incidents for each driver. To calculate risk factor for the drivers, we'll need their total miles traveled, which we can get from the driver mileage table we created in Hive. So we'll load the driver mileage table the same way we loaded geolocation, using the HCAT loader. For us to finally be able to calculate the risk factor, we'll want both the total number of occurrences and the total miles traveled for each driver available in one variable. In our pig helper, we'll go to relational operators and select the join function. The data in variable E contains the total number of occurrences for each driver, and the variable F contains the total number of miles traveled for each driver. The join function will make sure both of these pieces of info are available from variable G. We're now ready to calculate the final result. In final data, we'll iterate through our join data in the variable G and create a new variable where each row will contain a driver ID, the number of events for that driver, the total miles traveled for that driver, and the risk factor for that driver, which we'll calculate by dividing the total miles traveled by the number of events for the driver. Once we have our final data, we'll want to save it back into Hive. So we'll store our final data into risk factor using the HCAT store. In order for us to use the Hive catalog functions, we'll need to make sure we add the argument useHCatalog. Simply paste it into the argument text box and click Add. Before we run the script, let's take another quick look at what it's actually doing. We're loading the geolocation table from Hive. We're filtering out all the events from it that aren't normal. We're creating a new column to help us sum up the events. We're grouping all the events by driver ID. We're summing up and storing the total number of events for each driver. We're loading the driver's total miles traveled. We're joining the two tables containing the number of events and the total miles traveled for each driver into a single variable. We're then calculating risk factor from the joined data. And finally, we're storing our results into a pre-existing risk factor table in Hive. We're going to go ahead and run the script and ensure the result is what was expected. It appears to have finished successfully, but we'll verify it in the logs. Once we scroll down far enough, we can see that the run was a success. We can also verify that it successfully loaded the entries from the geolocation table and the entries from driver mileage. And finally, we see that we successfully stored 9,900 records into the risk factor table. Let's go back to Hive and do some additional verification. Back in Hive, we can perform a simple select on the risk factor table. The table has everything we expected to see. It lists all of the driver IDs, the number of non-normal events each driver had, their total miles traveled, and their risk factor. We're now going to generate the same table using Spark instead of Pig. To use Spark, we'll go back to our Symphony homepage, select the Web UI drop-down, and go to the Zeppelin notebook. From the Zeppelin homepage, we'll select Create New Note and call it Compute Risk Factor with Spark. Before we begin computing risk factor, let's list the tables using JDBC. We can see all of our Hive tables, including the risk factor table we created in Pig. We'll need to drop our old risk factor table so that we can ensure that the data we create in this section is actually coming from Spark and not left over from Pig. Another quick show tables reveals that risk factor has indeed been dropped. Before we can begin manipulating data from Hive tables using Spark, we'll need to create a Hive context. The context will be stored in our Hive context variable for easy access. Now let's use our Hive context and list our tables. Though not in the prettiest format, our tables and whether they are temporary or not are all listed. To begin computing risk factor, we'll need to load the pertinent data into temporary tables. We'll start with creating a resilient distributed dataset, or RDD, by selecting everything from the geolocation table. We'll also need to create an RDD by selecting everything from the driver mileage table. The data inside of an RDD is immutable and cannot be used as though it were a table. So we'll need to write the data inside of our temporary geolocation and driver mileage RDDs back into temporary tables so that they can be queried. We'll perform a show tables afterwards to ensure our temporary tables were successfully created. We can see that our geolocation and driver mileage tables were created and marked as temporary. They will be dropped after the session is closed out. We can now perform queries against these temporary tables. We'll start by querying the temporary geolocation table and filtering out any event that is not normal. And then we'll perform a count on the number of non-normal events for each driver ID. To be able to use this filtered data, we will need to write it to a new temporary table. We'll call the new temporary table geolocation temp2. And we can see that the new temporary table was created successfully. Let's show 10 entries from our filtered table. As we would expect, the table contains a list of driver IDs and the number of non-normal occurrences each driver has had. We'll now perform a query that will join the data we're interested in. So for each driver ID, we will create a row with the total occurrences and the total miles from geolocation temp2 and driver mileage respectively. Create a temp table from this new RDD and call it joined so that we can perform risk calculation on the data within it. And again, we confirm the table was created. Let's ensure the table's contents have what we need for calculating risk factor. The table contains driver ID, occurrences, and total miles, which are the minimum pieces of information we need to calculate risk factor for each driver. Since we have the information we need, let's go ahead and create the RDD containing our risk factor. We'll select driver ID, occurrences, total miles, and the total miles divided by the number of occurrences, which gives us our risk factor. And we're getting all of this info from the join table we just created. Once more, we'll write the RDD data to a temporary table and call it riskfactor.spark. And then of course confirm it was created. Like all of the other tables we've created, we'll want to confirm the table's contents. As expected, we have our driver IDs, occurrences, total miles, and the driver's risk factor. We're now going to create a blank Hive table, and we'll call it final results. It will have a driver ID, occurrence, total miles, and the risk factor. The table will be stored in ORC format, so it will be optimized for large streaming reads. It will also allow us to specify the type of each column for more efficient table searching and manipulation. Our new blank table appears to have been created. Now we'll populate it. To accomplish this, we'll write the risk factor spark RDD in ORC format to a file in HDFS called riskfactor_spark. Once our file is written successfully, we'll want to load the data from our riskfactor_spark file into the final results table. And finally, we'll create our risk factor table by performing a create table as select on the final results table. With our new table created, let's go back to Hive to verify the contents of the table. We'll perform a standard select from risk factor and return 10 results. And as we can see, the results contain the driver ID, occurrences, total miles, and the driver's risk factor as expected. This concludes the demo portion of the video. Let's review what the analytics pack will get you. You will gain instant access to an entire Hortonworks data platform, including all of the tools we used in this video. As with all mission packs, installation is extremely easy. Once the pack is installed, the components don't require any additional configuration to function. Just log in and all of the tools are ready to go. The VMs and tools installed with this mission pack will all be configured in their own security group, and all of the network rules that govern how they communicate with each other and your other components will already be configured. Installing any mission pack will not affect your ATO status. All mission packs will be ATO ready before they are released to any customer. I hope you found the information in this video helpful. Thanks for listening. Symphony, where accreditation meets automation.